Thank you, and thanks to all of you who are sticking around to this last talk. I'll try to make it entertaining and quick. So I'll repeat some of that introduction again, but I'll go quickly through it. So I'm a software developer with OS and virtualization background. I studied at the Technical University in Dresden, which is the home for something called the Nova microhypervisor. Without going into too much detail, but microhypervisor is a very tiny operating system kernel that's been designed with virtualization in mind from the start, and it only implements the necessary mechanisms in the kernel mode, and then everything else is built on top of that in the user land. As mentioned, I've worked with Intel and FireEye, where we try to apply virtual machine technology in security-related areas, for example, endpoint protection or malware analysis. After that, we decided to found this company, Cyberus Technology, where we wanted to bring something on the market that features Nova at its core. And that brings me to the motivation of this talk, which is our Tyco malware analysis platform. And again, I won't go into too much detail, but the platform looks like this. We have the analyst's laptop on the left, which contains your usual work environment like IDA Pro, debuggers, volatility, static analysis stuff. And then you have a target that's connected to it that basically runs just a normal installed Windows system, unmodified, and then we just slip our hypervisor and the virtualization underneath, and we use it to analyze malware. Now, the question is, what do we actually analyze in malware? And that's the application behavior. So we have this application that's usually to do something that is useful to the application. It accesses files or the network or the Windows registry. And the way to do that on pretty much every operating system I know is system calls. And so a system call is just the interface between the kernel, the operating system kernel, and the application that wants something done. So the operating system is there to service requests that are signified by system calls. And these include stuff like file access, network access, all those things that you want to control as an application, including starting processes, threads, and modifying your memory layout in the application. And for the rest of the talk, we'll be using one system call example to see how we interpret this in our analysis platform. And again, you don't have to look too closely. This system call will haunt you for the rest of the talk. This is how the system call looks like on IDA Pro. You just have something here that's the system call instruction, and then you have just a bunch of numbers, ones and zeros, and nothing makes any sense. What we actually want is a picture like this. So we have a printed output of the system call parameters of what this is actually about. We don't want to look at all those numbers in detail all the time. And the way from the previous image to this one will be what I'm going to be talking about in this talk. But first we have to feel some of that pain. So we do that manually first, and then see how we can automate it. And first of all, we have to think about how we interpret a system call on the Windows machine. And one of the key things is we have to find out which system call it actually is. And that is stored in a register called RAX on the 64-bit Windows. So that we actually know. And we also know that the result of the system call after it was handled is also stored in that register. And then the system call on Windows pretty much follows the Microsoft calling convention. So we have 4 registers, 4 parameters. This is RCX, RDX, R8, and R9. However, on system call that doesn't really work because RCX is used internally, so that is swapped with R10. But still, we end up with these 4 registers for the first 4 parameters, and the rest is just passed on the stack. But for the rest of this talk, to make it simple, we just focus on the register ones, so it doesn't get too complicated. So, what do we need to know in order to interpret the system call now? We need to know the Windows version. For example, we have a Windows 7 Service Pack 1. And then we need the architectural state, which contains the registers that we've been talking about. And we also need the memory dumps. And both of them we need before and after the system call, so we see what went into the kernel and what came out of it. Now, coming back to the example, we have this register state now in a little bit more readable form because I've already highlighted the 4 parameters for you and also the number. Now we see it's hexadecimal 52. And we have 4 parameters that still don't really make sense to most of us, I guess. And what we also know is after the system call, the result is 0. So yeah, it's the first information we understand. It's the error code 0, which is success. But all the rest is still pretty much unclear. We have to figure out what system call was that and what parameters went in. Now, how do we find that? Of course, as usual, the internet knows things. There is, for example, the Microsoft developer documentation. Unfortunately, that's pretty incomplete when it comes to those low-level system calls. And that's also partly on purpose, because that's something Microsoft usually wants to hide, because they have their own system call wrapper libraries like NTDLL that contain all the wrapper code. So you as a developer don't have to worry about it. You just call a function and out comes the result. But for us, from the hardware low-level perspective, we have to deal with this low-level system call, so we have to find out what it's all about. And of course, we're not the only ones. There are third-party websites who gathered this information and presented it. And I'll give you 2 examples. One of them is vexillium.org, which contains a system call list for all the Windows versions that this person found and the respective numbers for the system calls. And then there's also something called undocumented NT internals, which contains system call signatures for most of the system calls we're looking at. So again, coming back to the example, we can do a first assessment with those websites. And we have the signature here for NT create file, because this hex 52 that I've shown you earlier actually corresponds to NT create file on Windows 7. So now we can make sense of the parameters. We have the first one pointing to a file handle that will be the result of the system call. And then we have something called desired access, which is the access that the application wants. And we have object attributes, which is again a pointer. We'll come to that in a bit. And then we have another parameter that is just there for completeness because it's the 4th one. Now, as I mentioned, there are pointers in there. So to interpret what's going into the kernel, we have to follow that pointer. For example, this object attributes thing, because we want to make sense out of it. So we take this number and we take this pointer to the data structure, read it from the memory dump, and then kind of have to make sense out of it. But what's the structure layout? We have no idea again. So we also need type information in addition to this signature of the system call. But the previous page that we found doesn't have this information again. So we're looking somewhere else. And where do we look? If any one of you is familiar with the Windows debugger, they will know that the Windows debugger has these type information. But where does it get that from? There's something called the symbol files, the program database files. And these contain type information. And luckily, we can download them from the Microsoft server. And again, luckily, there are parsing libraries for Python that can just interpret that file for us and give us the output we need. And I have to warn you a bit, there's a lot of text, but I've highlighted some of it again. This is what comes out of the program database file. If we look at this signature and the object attribute structure, that's actually the one at the top. And the one I'm particularly interested in today is the object name, which is at a given offset within the structure, and it has a certain type again. But this type is, again, something non-trivial, so we have to reinterpret the PDB file and find that type inside, and that's the lower part. This is actually the Unicode string type. In Windows, that's, again, a structure that contains the length and a pointer to the buffer of that string. Now, with this knowledge, we can actually go into the memory dump and see what's in there. And this is looks like this. We have the pointer to the object attributes, which is this one. And at the beginning, we have the length. That's not too interesting. But then at offset 16, so the second line, we have an 8-byte pointer. In this case, little endian, so we have to read it backwards. And we end up with something 22F410. So we go again into the memory dump and read that part, which is this one, the Unicode string. And again, at the given offset, we have an 8-byte pointer, read it backwards. We have 2D1A80. We go into the memory dump again, and finally read the string of the object name attribute, which is some startme.bat file in the administrator home directory. Those of you who already met us at the booth, they will know this string already. The rest of us, maybe you will find out later. And now this decoding the memory is quite a cumbersome process. We have to do it. We have to find the memory location. We have to decode a structure. So we have to find out what the structure is, what it looks like, what members it has. And then we have to follow pointers again. So we do the whole thing over and over again until we find the information we actually want. And once we've done that, even if we write it in a script, it's going to be pretty tailored to the specific system call we're dealing with. And if we have to decode the next system call, we end up doing most of it again, or at least modify it. Now, to write a generic script, we would actually need something machine-readable, like a lookup knowledge database. And this is what we've built. So, to remind you, what we want is to go from ones and zeros through one interpreter module to something like this nice picture that just shows us our information. And this is where the main core of this talk comes into play, which is our OS internal scraping toolkit. So we've seen all this information on the internet, and what we want is we want to take it all in and munch it up, and then out comes the knowledge base that we can use in a script. So we take these sources that I've talked about, the internet and the symbol files, and also sometimes we need some custom knowledge to make sense of out of all of it. We throw it into this scraper and parser for the PDB files, and what comes out is a knowledge database containing the system call, definitions, numbers, and also the types. And the current sources we have for this are the aforementioned Baxillium.org for the system call list of numbers, and we have the NT-internals website for the signature definitions. And then we also have the symbol files from Microsoft for the type definitions. And now I'll show you how this output knowledge base looks like. First of all, we have the system call list, which is just a normal table mapping the system call name to the respective number on the Windows version we're dealing with. As you can see, sometimes the number is different in different Windows versions, so we have to deal with that. Then once we find the corresponding name for the number, we have to, look at the system call signatures, which is represented in JSON in our case. And that's just a list that maps the system call name to a list of parameters that it takes. And every parameter is described by the direction. So if it's going into the kernel, out of the kernel, or both, it describes the type and also the name of it. And this type that is in there, we can actually look up in the type definitions. That's the third output artifact we have, which is just a map from from the type name, for example, object attributes, that maps it to the length of the structure, and then all the members that are again described by their name, the offset, and the type. So we can go recursively and find in the object attributes the Unicode string, and then find the Unicode string in the same file and see what's in there. Now with all this, we can do this painful manual interpretation I've shown you earlier, just in one script. And the script looks like this. By the way, you can download the entire presentation and the example together with dumps to play with it yourself with this URL. It's also on the summary slide. And what you can see if you run that script on the register states and the before and after memory dump, you see that it's the NT-create file system call. It finds a parameter going into the kernel that's called desired access. It's a bit mask. And then it finds this object attributes pointer. So it will follow that one because it's a pointer argument. It'll decode it by looking it up and say there's a length parameter, root directory, and then it finds this Unicode string, which is again a pointer, so it follows it, and it prints this name that we've seen earlier, and then it just goes through the rest, which is not too interesting, but it will also find then that the system call has a result of 0, so we're now moving to the afterwards interpretation, and one of the output parameters, if you remember, is the file handle, which is again a pointer, so it follows it and says the handle is hex 34. And then just for completeness, it also outputs the rest. Yeah, so this also looks, already looks quite nice. But there is always, when there's some good, there's also some bad and ugly involved. So as I've mentioned before, maybe you've heard it, there are some missing entries because this NT-internal website only has documentation for most of the system calls we're looking for. For example, I was looking the other day for NT-OpenKeyX, and this one was not included in the website. There are also sometimes some inaccuracies in those websites. For example, there is a missing pointer indicator in this system call when a combined input-output parameter is marked as ulong, when instead it should be pulong as a pointer. So we have to kind of deal with this in our knowledge base because it would be bad if we look up the wrong type. And that's why we have some Quirk infrastructure to deal with these corrections, at least until after we've reported it to the website maintainer. Until that is fixed, we have to kind of deal with it locally. Which brings us also to the next steps, because of course we want to add more sources to this. We want more coverage and more accuracy. And one example that I've left out earlier where we can find stuff is source code of Windows-related projects, because those projects already have this kind of information in them. They implement part of this interface, so they have to know it. And that's why we want to look at stuff like ReactOS, Wine, or Process Hacker and parse their source code or use some part of their knowledge base to include it in ours, or maybe merge them at some point. And one other thing is, if we build something like a scraper, we don't want to do that all the time because maybe there is no update. Maybe the updates are wrong. Maybe the updates are incomplete. So we want some kind of versioning and update checker. And what we also want is more operating systems, because currently we only support Windows 7 64-bit, because that's the one we needed. Of course, it would be nice to include all the other operating systems as well. And the result of all of that is we realized that there is no such thing as the complete knowledge base on the internet yet. And part of the reason is that everyone just builds their own little stuff that they need and then they're happy. So we decided to open source this part, and we've already announced this. This knowledge base generation is available on our public GitLab account. And what we're hoping for is to engage with the open source community and make this better over time. And there's another thing. We're running a little bit late, so it might not be possible, but thanks to all of you who have already participated in our Tiny CTF challenge, we had a live setup there where you can play with this system call interpretation live on a running system. Now, to summarize this, and then we all can go into a nice evening and have a beer. We've seen that interpreting low-level system calls is very hard and annoying work. And part of that is that the information is scattered around the internet and it's difficult to find and it's cumbersome. But then what we've also seen is that once you have the nice knowledge database, scriptability really can rock, and you can build something nice that can be applied in a generic way to every system call you find. And then we also hopefully establish that open source rocks, because we can just all profit from this effort and hopefully never do this again. So, as I mentioned, we have this on our public GitLab. The presentation and the example can be downloaded here. And if you need anything more or want to get in touch with us, there's our Twitter handles. Mine is Kleparty, and we're Cypress Tech. And with that, I'd like to thank you for the attention. And if there are any questions, fire away.
So thank you, Markus. It was really interesting. Anyone has a question? Okay, so I do have questions. In the kernel, isn't there an analyst structure that would allow you at least to know whether at least the number of parameter of the syscall and some kind of type information about the syscall?
Where exactly would you find this?
I think I'm not a kernel expert, but I think I read that there is the syscall table inside the kernel structure, but also an analyst table which is maintained in the kernel, so that when it goes into the syscall, it knows what kind of argument it expects. No?
I have to admit, I didn't hear of that, so it's worth looking into it.
I don't know.
It's a good hint. We don't have any data on this, I'm sorry.
Okay. Yes, and that was my only question, so...
I think everyone wants to go home now.
Maybe. Okay. So,
thank you very much.